for today. Okay, I think we'll go ahead and get started. Let me go ahead and open us up in prayer, and then we're going to go through some additional information that I think will be interesting. And as you all are working on your projects, I think you'll start to see what we're doing is interesting, and then what you're doing in your project, it gives a nice complementary sense of you actually using it. So almost like on-the-job training. So let's go and open up in prayer. Dear Heavenly Father, Lord, I pray that you would be working with each of the students in this course, Lord. I pray that the material will be clear. Pray that you would help them all to get a better understanding of what system engineering is and another aspect of engineering. In case maybe this might not be the area that they want to eventually focus on. Also, continue to help them in their spiritual formation, Lord, as they're completing their time of getting classes where they can be learning about Scripture and also getting a better sense of the theological concepts we wanted to be deriving from that and applying in our lives. Finally, give them interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Okay, so what we're going to do in our lecture is continuing on in our progression through our main textbook, System Engineering Practices, Principles and Practices. And what we're going to get in today is now going to be thinking about the functional analysis. And so this is the various micro steps that we're going through the concept development phase. But before I do that, I wanted to just back up a little bit, thinking about the requirements, because the requirements is such an important part of what we need to be doing and establishing a system. And so this is a diagram that is from our textbook that focuses on SysML, a practical guide to SysML. Freudenthal is the major author. And so this gives you another perspective of looking at requirements. And so here, this is trying to give examples of how different things relate to one another. And so we have like a requirements tree, but then there's other specifics here. And so this is a intruder detection system. This is one of the things that Freudenthal talks about, and we have talked about this a little bit when we were going over the use case diagrams. And so here we can see the operational environment. So this would be the title of the requirement. It is an ID number, which is S1, and then it gives the text of the requirement. The system shall be capable of detecting intruders 24 hours a day, 7 days a week under all weather conditions. Now we can see that there's things that are related to this, and so all weather conditions. And so now this is S1.1, and so this is one level below that, and the system shall be capable of detecting intruders under all weather conditions. And so this is, it's derived from the sensor decision. There's an interaction with the water spray test. This gets into the verification. How are you going to simulate all weather conditions? That's one of the ways that working with the customer, they decided to do that. And how is it refined? It's refined by the detection scenario use case. And so there's a mechanism that you can tie in the use case diagrams to a requirement. And plus there's also a state machine for a weather model. And we're going to be talking about state machines. That'll be one of the latter ones that we'll be getting a chance to explore. And so here we can see the sensor decision. The system shall use cameras to detect intruders. So this is specifying an implementation. And so sometimes that's not something that we want to be doing. You could be saying that the system shall be able to detect intruders, but we're not, even so, we're not specifying the type of cameras. So there still is a fair amount of trays that can be associated with that. And so this is the sensor decision that we're seeing these lower levels being spelled out. And also we have a derived here. Here's a requirement for all weather operations, and then that's satisfied by the camera. And here's another one that's being satisfied by the camera. And this stuff, we can see various relatedness that are coming up with that. So feel free to look over in chapter 13 of Freudenthal to get a chance to get some more insight on this. And so I went quickly over this, and I'll probably spend some more time doing this on Thursday, because in the sample model, I'll see these multiple levels of requirements, but this is from this textbooks, the space mission engineering, the new space mission analysis and design. It's a little bit over 10 years old now, but this is where these top level requirements are derived. And so start to think about with your requirements diagram, and I can start to spend some time in class on Thursdays during our lab time to have you share about what you have for your requirements and why you thought that was important. And so just to give you a reminder, so this is a space-based forest fire detection system. That's the overall requirement. And so I'll just go through a few. And so it needs to be an all-weather system, but there's a qualifier there. It needs to be able to work through light clouds. So if it's really intense cloud cover, then it's not realistic that it could actually perform. And so this is the level of refinement of what it can do in terms of its performance. I know Kyle is working on CubeSats or satellites in general. And so this is one of the things I'm going to be defaulting to, as well as thinking some other areas. And so now we're talking about a resolution, a 50-meter resolution. So if you have a little campfire at your campsite, this is not what it's trying to detect. It's trying to detect 50-meter, and so you can be thinking half of a football field length resolution. It also has this other area that is geolocation. So it needs to figure out within 1 kilometer exactly where this fire is located. And all of these things, these 3 requirements are under the performance area. So that would be a couple that I'll highlight, and then I'll just do one more, thinking in terms of the design life. And so for an enterprise level type of satellite, designing for 10 or maybe 12 years is common. 8 years is a slight reduction in that, but chances are it would go longer than 8 years. And so it has to be designed with redundancy and performance so it can go to, say, a 3 sigma likelihood that it'll last for 8 years. And so you can see you're creating a template that's going to be impacting a lot of the things that you're going to be doing as you get into more details with your design. So that's just a little bit of perspective thinking about that important area of requirements. Well, next, let's start to be thinking about the functional analysis and putting this in context. And so we'll have several figures in just a moment that will help us out. So we're in the process of selecting the system concept. And so the objectives of the concept definition phase are just to select a preferred system configuration and define system functional specifications. So we're getting into this functional level as well as a development schedule and cost. We're not going to be focusing so much in this class in detail of schedule and costs, but even like your project proposal, you've got a chance to be thinking about that to a degree. Concept definition includes the concept development stage, which lays the basis for the engineering development stage of the system lifecycle. It's you get into the defining a preferred concept, which also provides a baseline for development and engineering. And so the activities in this area are the following: performance requirements analysis. And so in our last chapter, we talked about requirements. You have at least 10 or so requirements. Now you want to be doing the performance analysis on that. So how does this relate to the operational objectives that the end user, the customer wants? We get into functional analysis and formulation. And so how we're going to allocate this into specific functions, and how are those functions going to be relating to components. I'll give an example of a coffee maker, also thinking about a car. And so maybe those would be some things that are helpful. Those are things that are discussed in a couple of our textbooks. Then we get into the concept selection, choosing the preferred concept by trade-off analysis. And so we can come up with several versions. And so maybe with Abby, she's going to come up with a 50 kilowatt hour battery option for a electric car, a 75 kilowatt hour option, and a 100 kilowatt hour option. Maybe those would be things that would then be traded off. And so if you have something that has 100 kilowatt hours, it's going to take a lot more batteries. It's going to be heavier. What is that going to do for the rest of the design? Maybe you're going to be taking away weight that you could be using for sensors and autonomous operation of your vehicle. Finally, you have to be thinking about concept validation. And so this is confirming that the validity and superiority of the chosen concept. Why does it make sense that this is the best option that you have selected? And so we want to be thinking about that level. So in the very beginning, we first couple of chapters, we had high-level versions of walking through the system lifecycle. Now we're getting in more micro steps in the concept development. And so here, last chapter, we were talking about concept exploration. Now we're getting into concept definition of the functional parts of that. And things that are in here are analysis of alternatives, sometimes called AOAs. And so this is where you get a shoot off between possible designs, and how do you figure out what is the best option to go forward. It's actually a fairly useful decision-making tool, something that I've used a lot in my career. Then you want to be figuring out the functional architecture. What functions do you actually need to be thinking about? And when I show you in a few slides a picture of a car and some of the different components, maybe that'll give you a perspective. And finally, after you figure out the physical, you're going to go to the next level. That's when you get into the physical architecture. So the system performance requirements that we talked about in the last chapter, these fold into that. And then you've had some candidate system concepts that have been explored. And now you're going to be doing a shoot off between those and saying, well, this is the first one, the highest performing one. And so maybe you're going to still keep 2 or 3 to go forward for a few more steps. So you have performance requirements in, and then you have functional specifications going out. So you can start to be defining the next level of functionality. And then you can also have the defined system concept. And so instead of just a general idea, now there's more substance behind that. And then this can start to feed into the advanced development. So we're moving along in this concept definition phase, system materialization. We did the needs analysis. We did the concept exploration. Now we're getting into the concept definition. And so each one of these, we get into more details. And so now we include the component level. And so we're defining the selected concept with specifications. We're defining the functional and the physical architecture. And we're also allocating functions to components. I know we're not dealing with a solar power system, but for example, recently I saw a show on This Old House, and it was talking about solar panels, and it said over the last 5 years that the production of electricity from the solar panels has doubled from about 10% efficiency to about 20% efficiency. So thus, with the same amount of real estate, you could actually be producing twice as much power. And so those are examples of things that are good to know. Maybe you didn't catch it in the first block of development, but in the second block, that would be something that you would want to take advantage. For Kyle working with satellites, this could be really instrumental because this would allow you to have twice the amount of power. So that would be a nice thing to have in your back pocket. So now let's think about the concept definition phase flow diagram for the concept definition phase. And so we have first we do the performance requirements analysis. And so we have inputs from things that have been done before, including predecessor system capability. And so what is the sweet spot that we need for the level of capability we're trying to do with this acquisition? Then we get into the functional analysis and formulation. And so perhaps there's functional elements that have been used previously, and so it makes sense to keep working on those. There's going to be trade-offs that are going to be taking place in this, and then you're going to be working out the functional requirements as a result of that. This is going to be folding into the preliminary functional design. We then can be looking at building block technologies. I just gave an example of, say, solar panel power generation has gone up by a factor of 2. And so this would thus be an enabler for things that maybe hadn't been possible previous to that. And so we can be having the functional requirements. Now we can get into a preferred concept, and then we can be doing some definition of that preferred concept. So maybe Nathaniel is going to start to get some perspectives on, well, am I going to be looking at upgrading a missile silo or doing a brand new one? And so what would be the benefits of just doing a retrofit of an existing missile silo or starting from scratch? And there's pros and cons for each one of those. You'd also have to be thinking about cost as an independent variable. And finally, in terms of the concept validation, well, we have these ideas, but how are we going to validate that we can actually do what we want? And so there can be simulations. You can be leveraging previous simulations, then you can be doing stuff for real. You have limited amounts of hardware. Maybe you might have some components that you're trying to explore. So this is just at this level, at the concept level, trying to do some validation and thinking ahead what you might want to do. Just like I mentioned before, the one quote that I like to use, system engineering is like insurance, you buy as much as you can afford. And the goal of system engineering is to try and find issues early rather than later. And the sooner that you find them, that's going to be helping out with reducing cost and making sure that you're going to meet your schedule. So in terms of functional analysis and formulation, the functional system building blocks are useful for functional definition. The selection of a preferred concept is a systems engineering function. So we're all plain systems engineers in this course. And so which formulates and compares evaluation of a range of alternative concepts. We have that also have the definition of component functions. So this includes functional building blocks and functional interactions. And we also have functional block diagram tools. And we're going to talk about a couple different types of diagrams in this chapter. And we'll get into that shortly. One way that type of diagram that you can be using for functional model structure is something called an IDEF0. And so you have your inputs on the left, the outputs on the right, the controls on the top, and the mechanism that feeds into this on the bottom, and then you define the functions. We're not going to really focus on this. An earlier rendition of this course, we spent more time going over IDEF0 functions, but for this version, what we're doing, we're not going to really emphasize that. And so, but at least wanted to mention that to give you a little bit of a context. Okay, so in our main textbook, we talk about in several parts of the chapter about making a coffee maker. And so this is the first of several charts. And this is looking at a functional block diagram. So what is it actually going to do? And so you can see this is more complicated than a use case. We can see that the user does various things. It receives the coffee material, it accepts the user commands, it provides status, and facilitates removal of materials. And each one of these are numbered. We're going to come back to this in a little bit. We're starting to define different specific functions that need to be accomplished. And there's like a flow of activity that takes place. So you have water and heat. You heat the water. The water drains through the coffee grinds and goes into the reciprocal here. And so all of these are part of the things that need to be fleshed out. And so this is one way of doing it with a functional block diagram. We're going to be doing something slightly different with a block definition diagram, but maybe the things that are listed here might give you some perspective. Well, there's also functional allocation. And so we have a general idea coming into this subphase, what we want to do, but now we need to figure out how to allocate these things in the best cost-effective, logical way. So developing alternative concept requires part art and part science. And so as a system engineer, you're part artist and you're part a technician altogether. And so it can be a very creative endeavor. Certainly the predecessor system can act as a baseline for further concepts, and that is assuming a predecessor is available. And for all the project ideas that you've come up with, that's the case. And it's usually a good place to be, especially when you're learning how to apply these concepts. Brainstorming and other team innovation techniques can assist in developing alternatives. I like to say when you're thinking about concept development that the laws of physics temporarily don't apply. And so you just want to be allowing those creative ideas to come in, influence you to try and think outside the box and use all of the various possibilities that can be out there. And so here we can see a sample functional to subsystem allocation matrix. And so say we're going to be targeting a handful of subsystems and we have functions. And so anybody want to make an observations about the utilizations of these subsystems? Does anyone see a subsystem that according to this transfer function that's not used at all?
D is instead of.
Yeah, I think I heard that. So basically you can see that this subsystem D is not used at all. And then you see that A only has one function that's taken place. B is heavily subscribed. E is heavily subscribed. So maybe this isn't the best allocation to subsystems. We have all this real estate and resources from D. If we were to do this, we would just be reducing it down to 4 subsystems. So maybe if I could take the load off and maybe have one of B and one of E applied to D, that would be a better way of applying the resources. This is another chart that's in our textbook, and it shows a functional category versus functional outputs. And so we have these things, and these are 4 things that the authors talk about a lot: is signals, data, materials, and energy. These are the inputs that are brought into a system or a subsystem. And what we start to do some manipulation of that, maybe it's changing the energy, changing it from 28 volts to 12 volts or 5 volts. Maybe the data isn't in the right format, that has to be fixed. The signals come in as an RF radio frequency, and we need to translate that to baseband. And what is that information? Is this coming from a sensor? And so all of these things then are into the guts of what we're trying to do. And then we do a transformative functions. And so we need to be translating, say, the energy from an engine to what a transaxle and a transmission needs if you're thinking in terms of a car. For Jonathan doing a nuclear power plant, you have to translate what is the stored energy source of a nuclear source, translating that into some mechanical way that's going to convert that to electricity. And so you can be thinking in terms of Nathaniel's missile silos. It's going to have a lot of stored energy, and the missiles that are associated with the payloads, the whatever the missile is meant to do, if it's a conventional weapon or a nuclear weapon. And so that could be, say, it's a liquid propellant, it could be solid propellant. What is the shelf life of that before it has to be replaced or retrofitted? And finally, we get the outputs for what we want to try and accomplish with our system. And so this is like a black box. For one of the big things that system engineers do is they try and provide the definition of what black boxes are at various levels. So this is a chart from the first chapter of Freudenthal, Practical Guide to SysML. And so here we can see that a car can easily be translated into these next level entries. And so if I was going to be forming a block definition diagram, these might be the things that I would want to be doing. And so we're starting to define functions. You have the wheels, you have the engine, the transmission. All of these are things that are differentiated. This is different than the coffee maker I mentioned earlier. I'm going to be coming back to that in a minute. But we also have the drivetrain. And so ultimately, it's whatever is applied to the wheels that's going to make the car go forward. So an engine, you need to have fuel for an engine. So if it's a gas engine, it's going to be gasoline. If it's an electric energy, the fuel is going to be the kilowatt hours that are stored in batteries, and then you would have an electric motor. An AC motor most likely would be the case of what you would have. That's going to be translating that in a manner that's going to drive the transmission. That's then going to translate that to the differential. So you're going to have two different wheels and a way of how to navigate things like turns and whatever. And so ultimately you're going to have that accelerating force. So this is where we're starting to get to the next level of definition of what we're trying to do with our design. I threw this in here. I'm also introducing, once again, another type of a SysML diagram type, a state machine. But here we want to be thinking about mapping requirements and analyzing a functional architecture. And so this is for an all-weather system. And so this is still focusing on this intruder detection system that's meant to be all-weather. We see a shorter version of a requirements diagram, and yet it's relating things from a use case diagram. And so you could copy and paste that and show how this relationship where it's refines. And so that comes in. We're also having a state machine from a weather model that's also used here to help refine this requirement. And so here we can see the weather model in more detail. And so here we can see that what are the states of a machine the weather model. And so it's either clear or not clear. And if it's not clear, then we come into here and then we have further definition. And so here we have a sub-state machine. So a state machine within a state machine. And so the possibilities here are it can be foggy, rainy, or snowy. And we can see that there's two levels of that. If it's foggy, then that's a terminal state. We have a clear state we're in, but we also have a precursor here, cloudy, and the possible things that could be going beyond cloudy. It could be rainy or it could be snowy. And so all of those are possibilities. And here we're getting a chance to be finding more of the capabilities we want to be capturing in our system. So from our textbook, these are more details of defining 3 functional analysis products versus the functional block diagram. So it identifies the system functions and the external organizations that interact with the system. It connect them together either internally or internally first. And so you need to be thinking what's happening inside, that would be internally, or externally, how it engages with external elements, and whatever may be more comfortable to visualize how your system interacts with the operational environment. There's also a functional flow diagram, and this is gets pretty close to what we're going to be exploring with an activity diagram. And so that's probably the first time you've heard me mention that, but that'll be something that's going to be coming up. So you identify the system functions and connect them using logic gates. Do the functions require all or just some inputs from previous function to execute the function? And then a sequence diagram, this is the name that's also for a yet another SysML diagram type. And so identifies the organizations, users, systems, subsystems, or components of the system concept. It connects them in time. And so this is a temporal relationship as your scenario starts. Do the interactions require unique input or all their multiple inputs? Similar for the outgoing messages, are there single or simultaneous messages that go out? So here we have an FBD, a functional diagram that's focusing on the internal. And so we'll be thinking about internal for a block in an internal block diagram, an IBD. And so I think you'll get a chance to be seeing how this would start to materialize when we start talking about that in probably about middle of our course. And so you want to be developing the internal functions. You want to figure out how to link those internal functions, and then finally link the internal functions with the external functions. And so we're going to get into that in the next companion diagram. So this is the internal view. Then we have an external view. So this is now develop all the external functions. So what do you share with outside entities? The car has to ride on the road, and so an external entity would be the road. An internal entity would be the translation of mechanical energy from the engine to the transmission. You want to link the internal and external functions. And so what are the internal drivers that drive the external function? And then you want to continue linking until all the scenarios are complete. And so the use case scenarios, this is how, if we were doing a complete exhaustive design, you would have to be looking at every use case diagram and make sure that it's mapped to requirements and functional things that are now laid out in your system. And so you can start to see that we're starting to get into a lot of details that need to be worked. So this is an abstract functional flow diagram. And so we'll be talking about activity diagrams that will talk about this. We may or may not, you can actually have these decision blocks in activity diagrams as well, but you can see that there's a functional flow that starts to take place. You have F1, F2, you have 2 things in parallel, and then it branches off into 2 things, they combine again. And so then when you've done those 2 in parallel, we then come down here, we branch again, do 2 things in parallel, and finally we finish up with F12. So this is an example of what are the things that have to take place for a coffee maker. And so as you start to be figuring out what you're going to do with the design, here we're doing a functional assessment before we get into those details. And there's a couple things that happen in parallel: distribute electricity, distributed heat. You need to warm up the water. You need to make the water available, so you're going to heat up the water. And then you can move on. And so those are some things. I'm just going over the ones that are in parallel. you provide the status, you facilitate removal of the materials, and you dissipate heat. All those happen at the end. Once you've done heating the coffee, you don't need to keep it heating. And so like the coffee pot, coffee maker my wife likes to use, it has an auto turn off feature, which can be nice so you don't end up burning down your house or something unexpected. So that's looking at it from a functional flow diagram. Here is it from a sequence diagram. You can be seeing the relationships of a handful of these functions. They go from the accept the inputs, and so the user turns it on. It then gets into the receiving the coffee materials. Then the materials are integrated. You have the heat being applied to the grinds, the heat being applied to the completed coffee to keep it warm for a certain period of time. And you can see there's like a flow of information or resources. You can also have things that are going in the other direction. So you can have like a bi-directional communication, a feedback acknowledging that this was complete. For a coffee maker, it's simple enough that some of those details say what you would want to be doing for Kyle Satellite, Nathaniel's nuclear power plant, Abby's electric vehicle, Jonathan's well, I think I got that all right. So Nathaniel's missile silo and Jonathan's nuclear power plant, all that has to come together. So then there's the traceability. And so this is every step you take, you're going to be coordinating with the requirements. And so you want to map the functions to the requirements and identify where there are either gaps or over allocated functions and requirements. If there are gaps, then a requirement has no supporting functions, or a function has no requirement and support. So if you don't have, if a function does not relate to a requirement, that's bad. And so you could argue, why are you actually doing that functionality? And even worse is you give a requirement that doesn't have a mapping to a function. This means that you're not doing everything that your sponsors want you to do. So this will either require the system engineer to find a suitable pairing or delete the function or requirement. If there are overlapping pairings, then look to decompose either the function into additional subfunctions or decompose the requirement to multiple requirements. And so you want to have that very simple set of requirements mapping to functions or subfunctions is the best way to do that. So this is just an example of mapping the functions to requirements allocation. And so this is for a different type of system. And so maybe some of you have been to the ER or you go see your primary care physician. And this is trying to annotate that patient processing methodology. And so this can range from any basic consultation to some folks that they need to be going through chemotherapy. And so this just tries to give you a sense of how that might look. Some have more requirements, but you definitely don't want to have a situation where there's no requirement related to a function, or there's no mapping of a function requirement to a function, or vice versa. Just okay, in terms of the concept development space, initially you want to say have at least 3. And so for each one of you, when you're in the middle of this process, trying to think of, well, what are the trait space? So for Jonathan with his nuclear power, there's various grades of nuclear sources. Some can be grades that would be ideal for nuclear power plants, and others it's refined further that you could use for nuclear weapons, which would not be something that you would want to use, but maybe there's some variation in those grades. The type of nuclear material, some last longer than others. How many silos are you going to make, or whatever you want to call each unit? nuclear power generation, just to give you an idea for one of the projects that you guys are working on. So you want to develop the correct concept, both in scope and level of details. And so you want to have the enough details that match what you're trying to do at that level of development. So right now we're focusing on concept with this chapter. It may require multiple perspectives to ensure that the team has considered the representative set of functions, interacts with the correct organization, systems, and threats, and operating in the representative operational environment. 3 of the 4 of you are in a terrestrial environment, so you could actually, to some degree, create a test environment for Kyle doing something in space. You have to do a mock-up of that environment to see what that would look like. Okay, well, we're coming to a close for this chapter. I decided to add some highlights to this chart, to the version that you have that I shared for the lecture notes, to maybe give some help to seeing a lot of this complex information for a relatively simple coffee maker. You have like 4 different types of decisions that you want to be thinking about. What is the size of the heating coil that you need? What is the size of the carafe? How much coffee you're going to hold? How much grounds do you want to contain and that you're going to process? And finally, what are the voltages? So maybe just to think about this a little bit here. And so how fast do you want to make it able to heat? So you want to be using a lot of energy or a little energy. Maybe there's a circuit breaker that would be a limitation that you want to pop the circuit breaker. But on the flip side, maybe some folks having coffee in a very short amount of time would be more important. My wife likes to have a smaller coffee pot, and so she likes having a smaller carafe, and so this would be the one that she would prefer. And so you need to be thinking about your audience. What type of a missile silo would Nathaniel like to be building? A smaller, maybe there's a more tactical type of missile, or a more strategic, larger type that could give a different type of decision. How much grounds? And so this is going to be related to the carafe size, but maybe someone wants to make really, really, really strong coffee. And so the container that holds the grounds is going to define that. And finally, the voltages. Maybe you're going to be making it for a US audience for 110 volts, or you want to make it a US European / international. And so having a 240 versus 110 / 120 voltage that you could handle. And so there's these possibilities that you can have. And so are you going to meet that, or are you going to have some way of not exactly doing it as well as you would like? And so partially you could fulfill it, or not at all, or it's an NA. So we're showing all the things listed down here, up here. And so this is just trying to show a comparison, interrelatedness of those possibilities. So that's a morphological box example. I really haven't used this in the type of things that I've worked on, but the various textbooks and things that I've leveraged refers to it. And so maybe the dialogue that I gave might give you some perspective to help out with that. So the things that we covered in this chapter, we talked about the selecting of the system concept, doing functional analysis and formulation. So we're going from requirements to functions. We looked at the functional allocations. You could have functions and subfunctions. We talked about the functional analysis products, various types of diagrams. We talked about the traceability requirements. So every function needs to have a requirement. And we also talked about the concept development space. So let me stop there and see if there's any comments or questions on what we covered. Is that good? You can also just give me a thumbs up. Okay, good. Well, that's all the lecture notes. I won't talk too much longer so my voice doesn't fade away, but I'll just I'll spend some more time as we do the majority of our lab work on Thursdays, but I'll just highlight a couple more diagrams. So this is from the other two, the other tool that I'm using that I have some more enterprise level capability. This is from Freudenthal, and so he created this model back in 2017 and wrote a book about it. And so the things that I'm focusing on here for this part of our discussion are requirements. And so you all developed 10 requirements. And I was showing you at the beginning of the lecture this high-level mission requirements summary. And so, but we can then actually go down various levels. And so this could be a very top level set of requirements. Then we can getting down more surgical into requirements, into mission requirements. And so this is for a space mission. And so then the layer below this would be doing the spacecraft. And so one of the things I've mentioned to Kyle, and you've heard me say this before we start to be talking, say, on looking at the power subsystem, we need to have a context for which we're going to be making a decision of like how much power would be required. And so, and what would be the resources that would impact that decision. And finally, we get down to a payload. And so here we can be seeing these various layers that start to come out. And so the top level, this was the table version. Here is the requirements diagram, the tree diagram that we have seen. And some of you actually did some sub-requirements. Others just had them all at that one level, but we saw some example with the performance. There were several sub-examples, and we can generate this table with the version of visual paradigms you're doing, but it's not going to be telling you any more details, so you're not going to be able to edit it. So then we get into the next level of requirements. And so here we can be seeing, okay, we need to be thinking about, well, what kind of launch vehicle am I going to be using? The James Webb Space Telescope, if anyone has ever looked at it, you might have noticed that the mirror, the collecting mirror, it actually folds up. And why they did that is because they needed to have it small enough to fit into a launch vehicle and what's called a fairing, the top of the launch vehicle where they contain the satellite had to fold up because there wasn't a launch vehicle that could handle it fully deployed. Okay, am I going to be working with a dedicated ground station, or is it going to be a common ground station? That would be something that you could be looking at. What's the mission life? What's the availability? So those are some things that you could be looking at. So that's focusing on this next level. I could also then look at the spacecraft specification. And so what is we can be looking at the physical characteristics. And so we have some larger sub areas. And so how much weight am I going to allocate here? What is the electric power? And so this is going to be the thing that Kyle would be wanting to focus on. What is the payload accommodations? How large of an interface is that payload going to have? If you think of a cube, is it going to have like one board and a 1U CubeSat? That might be something that would be falling out into that. Here we can see that the spacecraft would also be looking at, well, for general characteristics, how long is it going to last? I mentioned that for the one that, for this example, we were talking about 8 years being the goal. And so that's just looking a couple examples. And finally, looking at the payload level. Let's see if I can pull that up. Try to organize these right. So now we're just focusing on that payload sensor specifically. So how big is that physical sensor? Is it 1 kilogram, 100 milligrams? What is its weight? What is its power? And so sometimes this is called SWAP, size, weight, and power. That's just another acronym that's used in the space industry. What kind of sensing is it going to have? Is it going to have an electro-optic sensor, an infrared sensor, a is it just going to be an RF sensor? What spectral bands? What is its data rate? What is its field of view? These are all the things that would fall into the area that would need to be figured out for a payload. The interface has to be figured out, how much power, the mechanical interface, how is it going to hook into the interface. And so you see mechanical engineering here, electrical engineering that are things that get into more details when you think at things at that level. So I think that's a good place to stop with sharing my screen and trying to continue to give you the next level of details of what it means to think like a system engineer and actually go through this process. Any comments or questions? Are you guys following along with what I have there?
No questions.
Sure, Nathaniel.
Oh, no, I said no questions.
Oh, sorry.
No.
All right, well, I'll look forward to see you all on Thursday. I hope you guys have a good rest of your day. Take care of yourself. God bless.
Thank you.
Thank you.
Thank you.
Thanks.
Okay.